Hare Krishna. Hope you're doing well. Let's get started with this intense linear algebra question. And to answer it very thoroughly, you will need all sorts of knowledge on determinant subspaces. But to answer it quickly, you just need to pay attention to certain, I'm calling them transpose tweaks, but in general, attention to the structure defined in the options. And maybe you have already noticed the right answer over here, or which statement is not necessarily true. One disclaimer actually, if you quickly evaluate the options, suppose here if you take the identity matrix, then this is satisfied. Even here, if you start with the identity matrix, everything is one in the diagonal, you make one position zero, the entire matrix becomes singular. So this is also true for identity matrix. And this thing, again, if you take identity matrix and identity matrix like structure where you the whatever k many rows are zero, rest all have one in the diagonal, then you can make the adjustment to this k many rows, which is n minus rank k. If you make them one, it becomes non-singular. So this is also correct for identity. So intuition wise, it may be directed that option C is the incorrect answer, and for this question, that is why it is the correct answer, which is also the case, by the way. Option C is the right answer over here. But this is this is a slightly dangerous question because it is saying necessarily true. So just because it is true for identity in these A, B, D options doesn't mean that in general it is true for all matrices of order n, right? All square matrices of order n. So in these kind of questions, sometimes our intuition can go wrong also. And the way to solve these questions is mostly by coming up with counter examples to come to the the option which is not satisfying the necessarily true condition, because if you can just disprove it in one particular area out of the many infinite areas, you are done. But if you have to prove it, you have to prove it in every possible area. You have to give a general proof. And in competitive exams, our mindset should be more of a counter example mindset. Okay, but still, for the it gives the opportunity to look at good theory, so let's cover that. So when we look at this question, this option, I mean, the rank will be same if the row space is same, because essentially a matrix is a collection of row vectors, right? And so the space being spanned by these vectors is the row space, and the rank of the matrix is the dimension of the row space. So that is the row space, and there is a kernel space, and kernel space and row space are kind of complementary. So a matrix of order n can have maximum possible dimension n, and whatever is the dimension of row space and whatever is the dimension of the kernel space. So the intuitive thing to visualize the row space and kernel space is that row space is the actual information present in the matrix, whereas the kernel space is the emptiness in the matrix. So we essentially start with the kernel space side of argument for this. We take a vector from the kernel space. Any vector of the kernel space will satisfy this thing, that when you multiply the matrix with that vector, you get a null vector, and this vector x curl is non-zero, by the way. It can be written as this. This means if x curl is the vector for kernel space of a to the power 7, ax curl is the vector for kernel space of a to the power 6. But in the question, in this option, it's already given that the rank of row space is same, which means the rank of kernel space will be same. And the kernel space, not just the rank being same, the kernel space itself would be same. And that's how we essentially come to transformation of this thing to this thing, which means ax curl is also this kernel vector for a to the power 5, but that means a to the power 6 x curl is 0. So we started with this and we came at this. This implies that the kernel space of a to the power 7 is a subset of a to the power 6, and the opposite is anyway true, that the kernel space of a to the power 6 is a subset of a to the power 7. This is a general thing. As we keep on increasing the matrix powers, we have this thing that whatever is the kernel space of a to the power k plus 1, that will be a supersetish structure of the kernel space of a to the power k. So both these make the kernel space the same, which means the row space is also the same. And that's how we know that this is true. For this one, it's also interesting. We can, okay, when we have a matrix, let's take the 3 cross 3 matrix, any general 3 cross 3 matrix. How do we compute the determinant? We can start with any row, fix this thing, then partition it and look at the determinant of this thing. We take a1 multiplied by a11 multiplied by this cofactor c11 plus then a12 multiplied by this c12. When it comes to a12, we take the sub partition of this thing and this thing, and for a13 we take this determinant. So the point is, any row, uh, the determinant can be expressed as this linear combination of elements of any row, and because the determinant is non-singular, we have this as whatever quantity, and all we need to do is isolate the sum. Let's say like this. This is equal to determinant A, let's call it dA, and we take this thing on the other side. So this becomes dA minus this thing, and we can find an observation for without loss of generality. I'm taking it the first observation only, where if we make this adjustment and change a11 to this dA minus the rest of the summation divided by c11, then with this modification this thing will add up to 0, right? And that's what we do. That's how we have a general proof that by tweaking one element, where the value will be adjusted as per the cofactor structure of the determinant, we can get a 0 value for the determinant. That is the intuition about it. For this one, the general proof is slightly more nuanced, where let's say we have R as the rank of the matrix A. So we can write the matrix as a combination of these column vectors, where the first R are linearly independent. And what we do is, for the remaining CR plus 1 to CN, we transform the column to be the sum of this thing, where EJ is the basis vector, uh, where we have jth element as 1, others as 0. And what this does is you get a new matrix like this, which is this thing. Now, if we take this summation equal to 0, essentially the sum of the column vectors, linear, any arbitrary linear sum of the column vectors to be 0, then each of these C curl R plus 1 to C curl R n will be the sum of Cj plus Ej, so they separate out accordingly. Now this first part, it's completely contained in the subspace of C1 to Cr, whereas this part is contained in a completely separate subspace of E to of this Ej vectors, where j goes from R plus 1 to n, and this is why this sum can only be 0 if every of these constants alpha j's are 0. Again, that it's kind of tricky because here it's the way it is becoming 0 is because it is a combination of one subspace which is completely separate from the other subspace, so they only interact at the null vector, and this is why this sum is 0. The pitfall over here is not catching properly why this is becoming 0. Again, it is two separate subspaces which can only interact at the null vector, so their linear combination of their vectors will only be the null vector if they are the constants are 0. It's kind of nuanced over here. And now, again, this may become a too long of a video, but there were just too many nice theoretical concepts to cover. And now, this sum could have been solved in maybe 10-20 seconds by looking at this structure A plus A transpose, and then your mind could click, okay, what matrices are connected with transpose, like symmetric matrix. Okay, but if I take the symmetric matrix identity, then rank is full, but A plus A transpose also has full rank. It doesn't tell me much about it. But another interesting thing is, how can I make this perhaps 0, less than n by 2? The best case less than n by 2 would be the 0 value. And that is when the skew symmetric matrix should click to you. That if you have A equals to minus A transpose, then the addition of that is completely the null matrix. The rank is 0. And from looking at this, you should connect to skew symmetric matrices, and then your final step would be to think of one skew symmetric matrix that is full rank, which is in two dimensions, the 2 cross 2 matrix, simply this one, right? It's a full rank matrix, but if you add it with its transpose, you get the null matrix. And again, this counter example, even if I show it for n equal to 2, it means this statement is not necessarily true, and that is it. So this could be uh, you know easily solved perhaps when you have a connection over here, because as I said in the start, like intuitively these options do seem sort of correct, right? This, looking at A plus A transpose triggering the skew symmetric concept, that is what gave the counter example. Yeah, the intuition is to connect the dots with nearby concepts. The journey from A plus A transpose to skew symmetric counter example, that was the heart of this problem. Take care. Hare Krishna.